Okay. Can you guys hear me?
Yep.
All right. Thanks. Thanks, TJ. And you could see the iPad, I assume. One sec. We'll start. Hi, everybody. 2004. What is it? 7304 as well. Tuesday, 11 a.m. And we're actually doing a lecture. I'm a bit afraid to ask if there are any questions because I think there'll be many questions. There's a visit hour today, 2 to 4. Is there somebody that has a pressing question that she or he cannot ask during the visit hour, or they have not sent me an email about? No, okay. So I assume I might see some of you in the visit hour. We should have 2 hours there. So I know it's a bit time consuming for you to listen into these visit hours, but I hope they're helpful. So the project is due tomorrow evening, end of the day. So now that I've pushed you away from asking questions, yeah, no questions? We should start. All right. So what we're going to do is we're going to hop on over to activity 6. So there's a few things in activity 4 that you, most of them with skim and skip, etc. And feel free to ask me about these things also in the visit hour. You might do that in the visit hour next week. For example, if you're going sequentially on activity 4 and have not read certain things, keep in mind, just in terms of, I know you want to do the right thing with the course. So you're going to have now, you're handing in project 1. Then later this week, I'll put out project 2, which has to do with continuous time Markov chains. We'll get through that. I'll push the submission deadline of project 2 a bit forward, just like we pushed project 1. And then there'll be the problem set. And with the problem set, you'll also get kind of a bit more of an indication where specifically in these activities you can kind of go and fill in the gaps. Okay. So we are now in activity 6. Okay, and that's dealing with the Poisson process. and I should shortly release activity 7, 8, 9, 10 in greater detail. So I'll update this document. So I hope we have a bit of fun today with this nice, neat chapter, SP2. Okay, so this is pretty much where we're living. That's a very readable chapter that has stuff that will stay with you for the rest of your lives. Poisson process. You can hear me now, right? Just want you to confirm that one more time.
Yep, no worries.
Yes.
Thank you. Good. Yes, there's this kind of, I mean, I wonder in this day and age how many lecturers have given a lecture just to themselves. I mean, it's probably happening right now around the world. You have some school teachers, some lecturers, somebody that's lecturing to their, and nobody's listening to them due to some technical trouble. All right. So what's a Poisson process? Very shortly, a Poisson process is a stochastic process of events that occur over time. And in the simplest form, just events of a single type. For example, here I'm out in the upper Brookfield. That's where I am now. I'm looking out the window, and whoop, a bird flew by. Whoops, there was a point. I'm looking out again. Whoop, another bird flew by. A second point. Okay, so I can plot these points on the timeline. So a realization of it might look like this is time, and we start at time 0. That's when I started this exercise with you. Up, a bird flew by, some time passed, another bird flew by, koala jumping off the tree. No, joking, that didn't happen. But these things are the points in time, and that's what a Poisson process is. That's it. And in a sense, you'll be convinced from this chapter that this is the most natural, or say the most uniform, but not in the uniform distribution sense, the most randomly possible way that you could speak about points happening like this over time, events over time. Okay, so Poisson processes, if you stand next to a radioactive material, something, please don't try this today, okay, and you stand with a Geiger counter and you get tick, like a proton hitting a tick, 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 it's the same. It's also a Poisson process, but it's also a good approximation for patients arriving to a hospital. Okay, so patient arriving, and then some time passes and patient arrives, and some time passes and patient arrives, etc. If we assume that we're during some given time of the day and things are stationary during that time. All right.
So is this going to be assignment 2, COVID hotel? So we've had the COVID hotel. Now we have the COVID hospital.
No hospitals. No. So assignment 2. Yeah, no COVID hospital. Yeah, and then the kind of the COVID graveyard. No, no. That's assignment 3, and that's actually, we should not joke about it. No laughing.
It's in very bad taste.
Very bad. And no, I mean, but in these times you need a bit of humor. No, assignment 2 will be about the SIR model, typically the stochastic SIR. Okay, that's roughly what it'll be about. All right, so exponential distribution. We're going now back to your early childhood and just reviewing a few facts about the exponential distribution. All right, exponential distribution plays a central role in the Poisson process. And you know what? The next thing after a Poisson process is the continuous time Markov chain. So when you want your Markov chain to run in continuous time, it's effectively using a whole bunch of Poisson processes in there. You could say a whole bunch of Poisson clocks. So the exponential distribution is kind of built in. Okay, so the exponential distribution. It's a random variable t, and lambda is a parameter. This will be the CDF. You might have seen this before. Not you might have. You certainly saw this before. This is what it looks like, the CDF. This here, the PDF. Okay, the density function, the PDF. Okay, this is a continuous random variable. Okay, this is what the PDF looks like. It has a mean here of 1 on lambda. So the expectation of this guy is the integral of t times the density lambda e to the minus lambda t, right? That's what it is. And you carry out this thing, integration by parts if you'd like. Okay, you do integration by parts. And this is an improper integral, and you get 1 on lambda. All right, that's a mean. You want the second moment? Sure, we can do that. We do second moments. You don't do a t, you put a t squared, you got your second moment. All right, you do some integration by parts. Again, you got this. You say, oh, what do I do this? Oh, this is like, again, this guy. You do integration by parts twice. Okay, but that's boring. You can do that though. That's 2 over lambda squared. That's the second moment. Okay, of course I'm going too fast, but this is just kind of a review of basic stuff you did in STAT3004 or some similar course. So the variance is second moment minus the first moment squared, and that happens to be 1 on lambda squared. All right, that's the variance. Okay, good. Exponential distribution. What else is there to know? All right, so if you take a random variable s that's exponentially distributed with parameter lambda 1, that's kind of what you'd call your standard exponential. Okay, so it's just like an exponential one. So it's really, I mean, the density is just e to the minus t. I mean, what a nice little simple density that is. Right, so, but if you scale it, if you multiply it by 1 on lambda, then you get your general exponential t. So, you know, just like you can scale a normal random variable by multiplying it by sigma, say, or dividing by sigma, depending what you want to do, here you can also scale an exponential. That's the whole point. Now, who forgot the lack of memory property? Get the joke? It's a good joke. It's like very funny. Okay, lack of memory property.
Is this the dementia property?
Is somebody calling it the dementia property? Yeah, that shouldn't be said. That's not funny.
Oh no,
Okay.
that's not funny. No,
all right,
sorry.
So
sorry.
No.
Yeah.
No, it's
No.
fine.
No.
Okay, thank you for having. I'm sure you hear me now. That's good. All right. So if you take an exponential line,
So I need to find some.
Actually, contain yourself. Yeah.
Yeah, I'm fine. No. I'm trying to think of something less controversial to call it, like lack of memory property. I could have called goldfish property, but apparently that's just a myth.
Going back to your ex-girlfriend property, I mean, there's a whole bunch of properties. I mean, there's, but okay, but come on, let's push on the Poisson. Okay, thanks for putting. Okay, all right. So, all right. I'm sorry for offending anyone. Of course, going back to your ex-boyfriend property as well. This is kind of a uniformly, you know, silly property. Okay, so if you think of t, if you think of the exponential random variable as a time between things, or the time until the next thing. Okay, so the time until the next event happens. And this condition is that that thing has not happened for the first little t time units. Okay, that has not happened for the first little t time units. And I'm asking, what's the probability that it will not also happen for the t plus s units? Okay, so if I write the intersection of that and that, that's actually going to be this, because the intersection of t greater than t and t greater than t plus s is t greater than t plus s, because the event t greater than t plus s is contained in t greater than t. And then you just have 1 minus the CDF, 1 minus the CDF, and that e to the minus lambda cancels, and you get e to the minus lambda. So the lack of memory property is that after something has not happened for little t time units, the chance of it happening again after t plus s is just the chance of it as though from the start happening, not happening for the first s units. Okay, so the process doesn't age. So that means immediately that, say, if I'm looking at, say, the lifetime of the motor, okay, some electric or mechanical motor that has moving parts, etc., and t is a random variable, its lifetime until it kind of breaks, or say breaks for the first time, but until it breaks. Okay, exponential random variable is probably not the right thing, right? Because as the motor has run for a while, there's probably some aging happening, and it shouldn't keep the same probability long. However, if you're looking at like a transistor, which is a little electronic device that has 3 little pins that appears also in microchips in a different form, okay? So until a transistor fail, you kind of, there's no real aging happening. Typically, this just kind of has to do with some, you know, random atomic blah blah that's happening there. So, and then an exponential random variable is probably good. Okay, but just that's the property of an exponential random variable. And one can also prove that if you're looking for continuous random variables, exponential random variables continuous on the support 0 infinity, and you say then I'm going to write this as an equation. I will write this thing equals this thing, okay? And I'll say what is going to be the CCDF of a random variable where this this green thing equals this green thing. Well, then it must be of the form e to the minus lambda s. Okay, so the exponential random variable is the only random variable on continuous random variable 0 infinity that possesses property. What's the friend of the exponential in discrete time that possesses this property? Discrete random variable that possesses property? Geometric. Thanks, Gabriel. Okay, right. All right. So good. We've got that going. I can stop moving now. Why? Sorry, sec. My pen. No. Okay. The next thing is an exponential race. An exponential race, and this will actually prove to be a. I'll already preview why this is okay. Why this is going to be kind of very important for us. So here's a. I'll get a Markov chain: state 1, state 2, state 3. Okay. I'm putting an arrow here. Okay, so you can move from state 1 to state 2, and from state 1 to state 3. Now, in the discrete time world, how does this thing work? You take the next time step. You live in discrete time. That's kind of by building, and you took here the probability P12, and you took the probability P13. Okay, and with those two probabilities, you either move to 2 or to 3. Maybe there was also a probability P11. Okay, but let's ignore this. Let's say there's no self transitions for a second. Okay, that was in discrete time case. What we're going to do in continuous time Markov chains that we're not speaking about today, but the exponential distribution is kind of central to that, and so is the Poisson process, is what's going to happen effectively is that we're going to be at state 1, and at any instance, we might make that jump to 2 or to 3. Okay, at any instance, we might go to 2 or 3. And that's much more appealing for most models, for most modeling scenarios for life, unless your models really live within days or within seasons. So unless there's really a discrete time component in the modeling story. Okay, so at any time you might go from 1 to 2 or to 3. It's going to turn out that processes that do this and possess the Markov property, effectively, there is an exponential time t here. Let me change color. T, do it like this. Okay, t. Until you go to time 2, and some other exponential time s, put this in a different color, okay, s, until you go to state 3. And what you're going to have at every time is you're going to have an exponential race between these two things, and more generally between a countable number of things, or at least a finite number of things if you'd like, right? So the exponential races are going to be kind of built in. But for that, let's not speak about Markov chains for now. Let's just go back and just speak about the exponential distribution. Just look at this property. You're now giving two random variables, and they're two independent random variables. Okay, it'll be hard to say something it's non-independent. And we're asking, what's the probability that we have that the minimum between s and t is greater than some specified little t? Okay, that now let me. Erase this kind of erasing on the Markov chain. So that's basically saying the time we're going to be in this state here is going to be, the duration is going to be minimum s of t. We're saying, what is the CCDF? When I see this, I call it the CCDF, the complementary cumulative distribution function. Okay, sometimes people call this, by the way, the survival function. Yeah, it's 1 minus the CDF. Survival function, people sometimes call this in stats. All right, and what's the CCDF of this random variable? So you've probably seen such an exercise before. So you say, well, this event occurs if and only if this event occurs, and the two things are independent. So then you multiply the CDFs, and you just use kind of this property of adding exponents, and you find out that it's exponential with the sum of the rates. Okay, so this is the key point. The sum of the rates, the sum of lambda plus mu, was the rate of s, and the rate of this was s, and this was t. Okay. Okay. All right. That's what you get with how long you've stayed here in stage 1. So now there's another question. Well, how long we've stayed in state 1 is one thing that's interesting, but the other thing that's interesting is, where are we going to go? Are we going to go to state 2 or state 3? Is t going to win, or is s going to win? So this here is a probability of s winning, right? That it was before t. Okay, so one way you could do this, you could put here on the ST plane, you could say you'd look at the joint density of these two things. So a joint density of two independent random variables is just a product of densities, and you're going to integrate out all this part. Okay. A different way you could do this is using this, which is the law of total probability. You'll say for every given value of S, and given value of S is f of S times d of S, well, we'll need for that t would be greater than that value of S. Okay, so you could do this computation in two ways. You carry out the integral, you go through a few steps, and you get to this. Okay, you get to this thing. So lambda divided by lambda plus mu. All right. So that would mean that would be the probability of making this transition. Okay. So that's these are two different numbers associated with the race. Okay. So let's just see it makes sense. So if you increase mu, so if you increase mu was a parameter of the exponential t. So increase mu, that means the mean of t is 1 on mu. That means that the means get very short. Okay. The means get very short. It means that this guy is much more likely to win. This guy is much more likely to win. You increase mu, you get this whole probability going down. Okay, because mu grows. Right. Okay, so S is not likely to win. I hope that's clear. You might have seen this in STAT. Okay. Now, you can continue. Here's an example that I won't speak about, but please read it. And you can continue this to n random variables by induction, for example, or in other means. Okay. And here's a theorem with these two facts that we've already stated, but we'll speak about the third in a second. So let V be, you're now taking I independent exponential random variables. Okay. V is going to be the minimum. So V is who won. No, sorry. V is how long it took to have a winner. V is how long it took to have a winner. And I is the random index of the winner. Okay. So you could say I is like a discrete random variable that tells you who won, right? So from these n exponentials, we've got these two random variables, V and I. Okay. So the CCDF of V is just exponential with the sum of the rates. The sum of the rates, that's an important thing here. Okay. So you say V is distributed exponential with sigma lambda I, okay? And the probability that the winner was I is lambda I divided by the sum. However, there's a third, or not however, in addition, there's a third important property that's very important, and that's that both I and V are independent. Okay, I and V are independent. So I'm teaching now, and you cannot come here. Dan needs to be on the other side of the building. Okay, we sent him away. All right. So I and V need to be independent. And you could show that by looking at these two. No, they don't need to be. They turn out to be independent. Okay. You could show that by following this proof. So it's basically looking at the joint distribution of this continuous random variable V and discrete random variable I, and seeing that it's a product of the distribution. So this property will turn out to be very important for continuous time Markov chains. It's actually not so, it doesn't play a role in Poisson processes per se. The way this chapter works, it starts with exponential distribution. Questions about this? Okay, I'm taking it that you've seen it in one form or another. Probably can't recall in the middle of the night, but I've seen it. Next thing that's quite basic is that when you sum up exponentials, you get a gamma. I mean, in fact, an exponential is a gamma, okay? So an exponential is a gamma with 1, comma lambda, okay? That people in the world of gamma distributions, what do people call this first parameter? This is like the scale parameter, scale. What do people call this first parameter in the gamma? The shape, yep. Thanks, Matthew, the shape. Without the question mark shape. Yep, the shape. Okay, so, and another name for a gamma with a discrete, I mean, this thing doesn't need to be discrete, this shape parameter, you can call it an Erlang distribution. An Erlang distribution is like a gamma with a discrete shape. Now, you might recall the density of a gamma function. I mean, of course you do, you're using it in other courses, etc. And here in the denominator, you have the gamma function of n. So the gamma function is a special gamma function. Go look it up if you forgot. Gamma function, okay? It's a special function, but the gamma function of a discrete value is just n minus 1 factorial. All right, just reminding you about that fact. I mean, gamma functions are in general, is a way to kind of generalize factorial to non-integer entries. Okay. Now, the result here is that when you sum up n independent exponentials, then the density of the sum is going to be this, and hence the sum is gamma distributed. All right? And you could prove this in one of several ways. You can do a convolution, and that's what's happening here. That's a convolution. That's not critical for our course, but it's critical for your general education. Or you can multiply the Laplace transforms or the moment generating functions and then see it's a gamma. Questions about this? No. Okay, let's get to business. Let's pick Poisson. So that was like a review of the exponential distribution, perhaps with the, I'm guessing that this fact was maybe a new fact that you've never seen before. That when you're doing a race, there's going to be independence between who won and what was their result. It's kind of nice, right? You're doing a race between these two exponentials, who won and what was their result. Who won is I, what was the result is a V, right? Let me do one more thing just to put this in context. So I spoke about continuous time Markov chains, but if you're not, but we still don't know what a continuous time Markov chain is really. So people often treat this in, say, reliability analysis. So now I said that, you know, maybe for a motor, there's a field called reliability analysis. So it's a field of engineering that relies on probability and statistics to understand the reliability of devices. Like, what's the mean time between failures of this device, right? So there's a few reliability engineers working in Apple that are kind of trying to estimate that, all right? So in a very basic setting, I mean, I said exponentials may be not good for a motor, but it's good for very basic components like transistors, etc. So you might have a system that's composed of n transistors, and you know, let's say the minute one of them fails, the whole system fails. There's no redundancy in the system. So V would be the random variable of how long it lived, okay? And it's going to be with the sum of the rates. It's going to be exponential with the sum of the rates. And I would be the random variable that tells you which one is the one that screwed it up for the rest of the system. Okay, let's speak Poisson. So this should update in a second on the screen. Defining the Poisson process. Now, the nice thing about this Poisson process is there are actually many definitions for it. And when you say many definitions, they're all going to be equivalent. So we're going to see here one of the definitions, but there are actually others. Okay, so sometimes people take things that are properties and then making definitions and show that it's equivalent. It's really a natural process. So, I mean, I bet you the mathematicians on other planets also know about this process. Okay, you just don't call it after the fish Poisson or the name of the person Poisson. Okay. We say that X has a Poisson distribution, just a random variable X, if it has this PMF, probability mass function. I mean, that's not a Poisson process, that's just a Poisson distribution. So again, a very basic review, you've done this before. And you can compute this thing for a Poisson random variable. What's this thing that I've highlighted? What is it called? What's it called? It's not the mean, it's not the variance. Factorial moment. Yep. Thanks, Nicholas. Factorial moment. It's a factorial moment. It's a k factorial moment. I mean, if k equals 1, it's just e of x. That's how you read it. If k equals 2, it's e of x times x minus 1, etc. K equals 3, etc. So the factorial moments actually have a very neat form, right? For Poisson distribution. But good. So we can do that also just by doing some summations and some stuff. All right. And from factorial moments, of course, we can get the variance. And it's kind of nice, the mean and the variance of the Poisson random variable are both lambda. So the mean is lambda and the variance is lambda. Okay. Okay. Now, some more properties, again, very, very basic. if you sum up k independent Poisson random variables, each can have their own lambda. These are not the exponentials anymore, they're Poisson, but the lambda is purposefully the same lambda. You'll see why by the end of this chapter. If you sum these guys up, you also get a Poisson random variable. Okay? Was the sum of exponentials exponential? No, it was gamma. The minimum of exponentials was exponential with the sum of the rates. Okay? So that's, get that clear in your head. And you can do this here. This is again a convolution, or you can do it by multiplying your favorite thing in the world, PGFs. Okay, so to take a product of PGFs and you'll get them. Okay. All right. Now that we know the Poisson distribution, which before you studied the Poisson distribution just as like a thing, you know, Poisson distribution, and you were told Poisson distribution is a distribution that measures the number of events that occurred in a given time interval. It's pretty good for that because it's like unbounded, right? The number of patients that arrive to a hospital during an hour, or the number of birds I'm going to see flying here on my right in a minute, okay? Or something like that. All right, that was just the distribution, but you didn't see y. We're going to see y soon. Okay, very different than say the binomial or the geometric, where you actually understood exactly what's happening with binomial geometric. Okay, so we're now ready to find a Poisson process. To do this, think about people arriving to an ATM. That's very bad. No, it's ATM. There's social distancing not happening at ATM. That's an automatic teller machine. People get cash. There used to be this thing called cash. Okay, so people get cash. They stand again, they get cash. Okay, and you look at the time interval 0s. Okay, so stand next to this ATM, 0s, or instead of the ATM, I'm looking at how many birds are passing. Okay, or maybe you guys are just looking at me for 30 minutes and saying how many stupid things I'm saying in 30 minutes. Okay, 0s, s being the 30 minutes. Okay, so number of events in time. Okay. So this process is now a stochastic process, just like you've dealt with other stochastic processes, branching processes, Markov processes, etc. It's a collection of random variables indexed by the time index s. Is a Poisson process if the following things happen. Okay, so first of all, at time 0, it needs to be 0. Okay, we kind of, you know, in 0, 0, nothing happened. Critically, the number of events during time, this is during the time s to t plus s, okay, this is this time interval, is Poisson distributed with lambda t. Okay, so the number of events during the time interval st plus s. I'm taking the time index. This is s, this is, let me write y t plus s, nice to write s plus t. Maybe this is of length t. So the number of events here is Poisson with lambda t. Okay. And so this thing is called an increment. Okay. So the increment to the number of patients that arrived in that interval, the increment to the number of birds that have passed through, the increment to the number of people that came to the ATM. And third is that for any collection of times, so I can take kind of the time axis and break it up in any way I want into n different times. N can be 100, 1,000, as much as I want. Okay, and I can take any arbitrary t's. These guys, this and that, and all the guys in the middle, these are increments. They're independent. The increments are independent. Okay, so if a process satisfies these things, it's a Poisson process. Now, this is actually not my favorite definition because you might have there's a different definition that actually does not require you to specifically specify the Poisson distribution. And the Poisson distribution comes out of it. Okay, all right, but that's first of all, if a process satisfies these things, it's a Poisson process. Okay, let me show you what a realization of a Poisson process looks like. So, you know, a random process is a collection of random variables. You can also think of it as a function. When I drew it up here, you didn't see, well, you'll get there in a sec. I'm just scrolling up. I could see on my laptop that it hasn't updated. So when I drew it here, you know, that looks just like a collection of points. But if I want to draw on this n of t, the Poisson process n of t, what I would draw, let me do it in red. I'll put start at 0, we go up to here, up to the first event. I put here a circle, then I've incremented by 1. Okay, that was like an open circle here. Let me actually delete a bit so it's just readable. Put an open circle. Then you go, there's no event, and then the second guy, go here, and the third guy. So this is a counting process. Okay, counting processes have realizations look like this. For a Poisson process, we want now the number of events during any time interval. Like I can take this time interval here, you know, I'll call this S, and this one here is T plus S. Okay, let me delete this S here. Okay, this is T plus S. Oh no, now my pen's not writing. I charged it. It's not good. Oh, no, it's right. Okay, T plus S. Okay. All right, so the number of events we had here, which in this case happened to be 1, the number of events that we had here, which in this case happened to be 1, is a Poisson random variable. In a different realization, we might have had something, I'll draw a different realization in purple. You might have gone like this maybe, and then maybe this, and maybe this, and maybe this, the next one, etc., etc. Okay, so that's what the actual Poisson process looks like. It doesn't look like those points on the line. It looks like this counting process. Okay, so and I drew 2 realizations, 2 random possibilities for the process. I'm scrolling back down. It'll take you a second to refresh. Okay. Now, to motivate the definition, questions? Okay. All right, so to motivate this definition, which actually puts in the Poisson distribution, it'll be good to think about what we call the binomial approximation to the Poisson. And did you guys see this in STAT3004? Or perhaps some did, some didn't. Sorry, STAT2003, or your previous probability course? Okay. Maybe even if you did, maybe it wasn't. Okay, so I'm going to draw a timeline here. It's again the same timeline we had before. Oh, okay, Gabriel said you saw it. Okay, so I'll speak about it quickly. Thanks, Gabriel. Okay, so and in this timeline, what I'm going to do is I'm going to break it into little slots, into little delta t's. Okay, that's what I'm doing. They're equally spaced. Okay, and there are going to be n of these slots. Okay, so I'll go up to some finite time for now, okay? Or I could just say that this is time s, and this is time t plus s, okay? So this is time of duration t. Okay, so I'm breaking that into n little slots. And with each slot, what I'm gonna do is I'm gonna have, with probability, with a very small probability, I'm gonna have an event, and with a non probability, I won't have an event. So I want to now count how many events there were, and the events are going to be independent. So when other probability, I mean the complement of the probability. So I'm going to have here like many n little independent Bernoulli trials. Okay. What I'm going to do is I'm going to make the chance of success in a Bernoulli trial 1 on n. Sorry, lambda on n, lambda on n. Okay. That's going to be like my p, my chance of success. So the more slots I get, as I make n smaller and smaller, lambda on n becomes, as I make n bigger and bigger, sorry, not speaking quickly, as I make n bigger and bigger, lambda on n becomes smaller and smaller. So p here goes to 0, okay? So basically I'm pushing n to infinity, and I'm pushing p to 0, but I'm doing it in a way such that p is coupled with lambda, p is coupled with n via lambda on n. What's the expected number of events in a binomial? The expected of binomial, you know, is n times p. So that's going to be n times lambda on n, so that's just lambda. So on average, I will have lambda events. And the chance of 2 events actually appearing in the little thing is, I mean, okay, with the binomial construction, it's 0, but in the Poisson process, it's also 0. So you don't, the chance of 2 things happening together is 0. So what you're going to have is this binomial. So a PMF, a probability mass function of binomial like this, that's indexed by n. If you take limit n to infinity on that, Okay, what you get is you get Poisson, and then you get Poisson lambda. So this relationship, the key to this proof is this guy, which has to do with the and that's an E. That's a typo here. Okay, that's a typo. It's not a 1. That's an E. Okay, it has to do with the fact that no, sorry, that's not an E. That's a 1. But it has to do. Sorry, this is. Okay, so it has to do with the definition of E as E is a limit of 1 plus 1 on n to the power n. And here, if you do a minus, you get an e to the minus lambda. Okay, so it's actually a simple proof. But the important thing is that what you think of here is you see that since a binomial distribution over a finite interval, when you take a finite interval of duration t, when you actually take n little slices, becomes a Poisson distribution when you make these slices infinitesimally small, motivates the Poisson distribution to appear naturally in such processes. Because look at me, I'm looking to my right, that's I guess to your left, and I'm looking, is there a bird coming, yes or no? So as a gross approximation, we can say that at every delta t, there might have been some bird here in the bush that's flying or not, every bird that's flying or not. Similar with the hospital, and then every little time, somebody's arriving, yes or no, completely independent of everything else. Of course, those assumptions at some point become maybe irrelevant, but as a first approximation. Okay, so that's that's how you relate the binomial distribution to the Poisson distribution, and that's why you would say that the size of the increment. I'll go back to this realization. I'm scrolling all the way to the top of the document. I see it takes a second to refresh. And that's why this distance of length t, you'd want that. So I'm calling this difference here nt plus s minus n of s should be distributed Poisson with lambda t. That's one way to motivate it. Okay. Constructing the Poisson process. So it turns out that in the Poisson process, the exponential distribution plays a key role. So we've spoken there about the exponential distribution, the Poisson distribution, the binomial distribution, and we're going back to the exponential distribution. Okay. So here is what we call, in general, this is what you call a renewal process. It's not written in this book, but I'll write it so you have it. Renewal process construction. Okay. So what's a renewal process? A renewal process is just like here, you got the point in time, you got time going to your right, and you've got these points, just like I drew before, point, they're a bit evenly spaced here, but the random times between the points. And this first random time is t1, the second random time is t2, the third one is t3, the fourth one t4, etc. And in your renewal process, you take these times to be IID. Okay, so it's kind of very simple. But on top of that, you can create the counting process, which we'll see in a second. That's just, I'm just going to understand this notation. All right. Now, a Poisson process is a renewal process where the times between events are exponential. But we'll prove that. We'll see that that's a property of the Poisson process. Okay. So in general, you can say that, if you didn't know anything, hardly anything about probability, hey, describe to me a process like this and what's sensible to put for these times, you might put like, you'd say T1 is uniform 0, 1, T2 is uniform 0, 1, T3 is uniform 0, 1, etc. Maybe you would have gone for uniform 0, 2, then they kind of have a mean of 1. Okay, so it's like these events that happen between things. Okay, the times between events. Sorry, events happen at times between events. Now, so they can be anything. They don't have to be exponential or anything like that. But it turns out that exponential is the natural thing in Poisson process. Okay. So if you have these events, you can then define the associated counting process, N of S, and you define it as follows. So, I mean, first of all, you need to define Tn, capital Tn, as a partial sum. So this point is T1, this point is T2, because it's tau1 plus tau2. This one is T3, because it's tau1 plus T2 plus tau3, etc. Okay, so you need to distinguish between the taus, which are the times between events, and the t's, which are the absolute times on the time. Okay. And then you'd say, now I'll give you some arbitrary point S, like they did this very nicely in this illustration. Erase this a bit. Okay. Arbitrary point S. All right. Tau 5 is not on this list. Tau 5 is this time, just so it's clear. So tau 5 is not on the point S. You're just taking some arbitrary point S. S could have also been here, or S could have been here, S could have been here. Okay. And now we say N of S is going to be the maximal N such that Tn is less than S. So this is the set of all elements N, all the indices N, such that Tn is less than S. So let's see, T1 is less than S, T2 is less than S, T3 is less than S, T4 is less than S, okay? T5 is not less than less than or equal. T5 is not less than S. So in this case, N of S, what's N of S here? This is an S. What's N of S? The maximal N, that's at the end, 4. Yeah, thanks, Matt. It's 4, correct. Okay, 4. All right. And if you move to from S to here, let's call this point S minus epsilon next to S. What's N of S? What's N of S minus epsilon, Matthew? Still 4. No question marks this time. Okay, good. All right. Even if you move to 4, even if you move exactly, so what's N of T of 4, Matthew? Matthew, you've dug yourself a deep hole here. What's N of T4? 4. Okay. Matthew, what's N of T4 minus epsilon? 3. Okay, no question mark. All right, no question marks, Matthew, never, just exclamation marks. I'm just joking. Okay, so good. So what you've done here is you've constructed the counting process, and you've exactly constructed this thing I had before, and it's important to now put these kind of closed circles, open circles. Remember what they took off points for you in math 1050, whatever, 1051. And you got a 6 and not a 7 because you didn't put a closed circle. I don't know if they really did that. Okay, clear, everything? Okay. All right, so this is how you define a counting process from just a sequence of times. All right. All right, now this is cool. Look, lemma 2,6. If you do this, so we started here with this renewal process with exponential times. Lemma says, if you do this, then N of S will have a Poisson distribution with mean lambda S. Okay, so the number of events during this whole time is going to be Poisson with mean lambda S. Okay. Oh, just kind of to set your mind straight, in the previous stat courses, you'd say Poisson with parameter 5, Poisson with parameter 3.2, Poisson with parameters always the lambda, the mean. Now, in a Poisson process, the mean will often have a time component multiplied to it, okay? Because lambda is the number of events per unit time, and S is the length of that time, okay? So the Poisson process doesn't have the mean. Random process does not have a mean. It might have a mean function, okay? Which we just found. The mean function is lambda S, but the random variable has a mean. So, you know, the mean function is just going to be this function which I'm drawing here, and that's just the linear function lambda S, okay? So some realizations will be above it, some below it. None would be exactly on it because these realizations are not continuous. This is the continuous linear function, okay? So how do we do this? So the basic idea is to, and this proof is actually important, okay? So we go back to what we had before, that we actually know the distributions of these guys. The distribution of T1 is exponential. The distribution of T2, what's the distribution of T2? You don't have to answer now, Matthew. There are 21 other people, maybe 19. What's the distribution of T2? Exponential. Isabel, you, so the distribution of tau2 is exponential. Okay, thanks, Isabel. The distribution of tau2, but T2 is tau1 plus tau2. So Isabel, what's the sum of two exponentials? So it's not going to be an exponential we saw before. It's, well done. All right, it's a gamma, right? It's a gamma. So T2 is gamma, or what we sometimes call an Erlang 2 lambda. Okay, that's T2. And then T3 will be gamma 3 lambda, etc. Okay, so we know the distributions of these times, okay, of the nth event, of the capital T. So this is now a nice thing to see. So the event that at time S you had n, okay, happens if and only if S lies between these two guys. Okay, if and only if S is greater or equal than Tn and less than Tn plus 1. Okay. So now you can look at the probability of this event, that ns equals n, some little number n. Oh wait, Matthew's asking, is Erlang used when you have a discrete shape parameter? Indeed, yeah. So Erlang was the inventor of telecommunication analysis in a sense. So he was a Danish engineer, mathematician at the start of the previous century. And about 100 years ago, or 110 years ago almost, he wrote one of the first papers that related Poisson processes and Markov chains, etc., to congestion of telecommunication systems. Something we luckily don't have congestion today. Our packets can actually go. So yeah, and then they named the distribution after him. They said, what distribution we take? Well, let's take a gamma and make the parameter discrete. Okay, but that actually happens very naturally in these types of processes, that you sum up exponentials. And so an Erlang is just like Matthew's saying, is a gamma with discrete shape parameter. All right, so the event ns equals n, what you can do is you can now do the law of total probability on the nth, on the density of the nth. Again, I'm writing law of total probability, I'm kind of summing over all the nth. Okay, so given that the nth event occurred at time t, okay, we would need for the n plus first event to be greater than time s minus t. Okay, n plus first event to be s minus t. This t should be a capital. This should be a capital T. That's a typo in the book. Okay, typos happen. It's a capital T. Okay. And now we can do this. So we stick the density of ftn is going to be this guy. This is this, and tn plus 1. Sorry, that's a mistake here. That should be a tau. Typos don't just happen; they happen in lectures. A lecture from Zoom, and they do this. So tau. Okay. Okay, so this is this density, and this is this probability. That's the survival function, or the CCDF if you'd like, etc. And you got yourself a nice integral. All right. Now you can massage this integral, and yada yada yada. One thing leads to another, and you get the Poisson distribution. So this is like subtle small point, but it's important. So you're saying ns equals n if and only if this happens and this happens. You can then write according to this law of total probability. Okay, so what we saw is that if you have a renewal process, I still we need to finish. So if we have a renewal process with exponential times in between, then the number of events of time s is going to be, it's going to scroll down for you in a second, the number of times of 2s, come on, you can do it, yes. Number of times of 2s is going to be Poisson with mean lambda s. And I'll just finish with this. The remaining other two lemmas, I have no idea what happened here, but that's nice. The remaining other two lemmas, okay, this one and this one show that this process will have independent increments, and this one that the increment is itself going to be Poisson distributed with a mean of is, so like this is, so these increments are also going to be Poisson distributed. And then NS is going to be a rate lambda Poisson process and will have independent increments. So in a nutshell, you say a Poisson process, you can now view it at least in two different ways. And I'm really going to finish. So the first way is what we actually put as the definition. Okay, let me now just erase a bit and summarize. So the key point in the definition was let's specify these independent increments and starting from 0, but most important, the Poisson distribution of this increment, of the counts of the increment. That was kind of the first definition, or a definition, according to this book. The second way was different. Let me erase some of this junk here, okay? The second way was, let's ask the times between events to be exponential, okay? And we will see that we get what adheres to the first definition. All right? So now when you physically think of a Poisson process, you can think of it in two completely ways. One is the counts, the number of events during an increment, or the total number of counts is Poisson distributed. Or you can say the time between events is exponentially distributed. So this section I won't speak about Friday, more realistic models, because 222 is skim. Just skim, okay? Poisson process is actually quite a realistic model, but sometimes you need a kind of a better thing. But what we're gonna do Friday is section 2.5, the transformations, okay? And I'll update activity 7, and we'll really define what a CTMC is, and that can actually also put you directly onto project 2. Are there any final questions or questions about this? Okay, so visit hour today at 2 till 4, and work well. So I think that's it. Thanks, guys. Bye-bye.
Jeremy.
Thank you.